As Gershon say, today, as Gershon say, we're going to focus on the solution that Siemens provide in NX for 3D printing, additive manufacturing process. Real solution that take place in one system end-to-end. It starts with design for additive manufacturing, continue with simulation for additive manufacturing, and end with the production of the additive manufacturing at a lot of machines. We will see it. Okay. Some of the slides, mainly just the two ones in Hebrew, but I will say it in English. I'm leading the engineering department at McKit, and I also lead some business activities. I have experience of more than 15 years with the CAD, CAE, CAM, and PLM system, and also NPI project and so on. 1 minute on McKit. McKit, it's we are celebrating 40 years in 2 years, and we are a very experienced company that have a lot of expert with in areas of CAD, CAM, CAE, and PLM, also civil engineering. And we are the only representative of Siemens PLM at Israel. We are involved at a lot of projects in all area of in Israel, the aerospace and defense, electronics, the academy, and so on. That's it. I want to start with simple use case that show the capabilities, how we start. I will stop it for a minute. How we start to get the data, how we are dealing with the data, and how we can prepare it to simulation, to prepare it to additive process, and how we produce it. I want to start with it, and then I will go to the agenda, and we will continue. So what we are seeing now, it's a bone that was scanned and get into an X. This is an X. What we are seeing at the screen, it's an X. This is the bone, and this part was designed in an X. This will need to be some fixture on the bone, probably titanium. And what you will see in a few seconds that naturally an X perform operation with scan data. This is a scan data that doesn't go any reverse engineering process. And the click button in the system, we will see what will happen here. This calls convergent technology, and we will discuss it. The operation that you saw, it's a Boolean operation that calls subtract. And as you see in a click mouse button, we are performing subtract from the bone that scan and get into like LSTL and some other formats. And in mouse click button, the subtract is happening. Now we can see the continue of the process. We are putting the part on the build. If we need to generate support, this also can be achieved within an X, but right click button and we generate the support. And in this specific case, we also call this is the EOS print, printing titanium. We can see that we can review each layer and see if we have issues, and go to print. So what you saw here, you saw a full process that start in the X and end in the X. So this is the agenda for today, what I prepare, and if you will be interested after the session in more details, to do a deeper dive on every topic here, feel free to call me through Gershon or directly, and we can do this deep dive. Okay, so we will talk about the challenges and barriers that we see at additive technology. We will see the industrial additive manufacturing solution, Siemens solution. We will go through the design for additive manufacturing tools capability that Siemens proposed. And then we will go to the second level of the simulation for additive manufacturing. And we will finalize with the 3D printing itself, how to do the preparation of the build, how to do a nesting, 2D and 3D nesting, and how to build the support. This is the agenda for today. Okay. Okay, I also want to share with you this movie. In this movie, we can see the metal parts, metal components that go a very hard warm process. And in meanwhile, we can see in parallel this also small parts with the same material that go also the same process of heat. And we see that the small part is getting red, and the component that is with the same material doesn't get warm. How this process is achieved? This process is, you can see this project. I talk with Gershon, and Gershon say, present a problem and then present the solution. So this is one of the projects that can be talked. The problem here that the conventional thinking of the system is very complex assembly. The production of this assembly is very hard. You need to weld parts. You need to produce every part in an own and do an assembly, do a weldment process. And this whole chain is taking a lot of time and taking a lot of place. And also, it is very large system. And what Siemens provide here, it's a new thinking from conventional thinking for a conventional process, manufacturing process, to a new process with additive manufacturing. Perform simulation of flow like you see here, simulation of topology optimization, simulation of design space, and then you can go and seek for the optimized optimized component that, as you saw, Jack is putting his hand on the material after a few seconds and it doesn't get burned. So this is the end. In the end, you can see this is what was the first. This project was, this was the dimension before, and this is the dimension after. This is the dimension, and of course, we have reduced in weight, we have reduced in lead time, we have reduced in weld process, and we accelerate, of course, the business. We accelerate everything in every area. This is first example. The second example is what you're seeing here. The second example in the conventional thinking was a system or subsystem that was built with something like 13 parts, 13 components that was need to be assembled together. Also need to be some weldment here and so on. But Siemens take this project, and the goal was to lower down the lead time, lower down the weight of the component, and this was achieved by rethinking the business, rethinking the technology. So from 13 parts, in additive manufacturing, we are printing one part, as you see here on the screen. And after that, we also need to complete the process with machining, like turning, like milling, and grinding to achieve the final dimension, because this is very accurate parts. This is very accurate parts, this sub-assembly, and this sub-assembly goes to here, to this final assembly. So it needs to be accurate. Of course, it needs to be without any fluence, and you will see also during the presentation how we can be assured that we are printing right the first time. So what you're seeing here, we go from 13 parts to one part. So the system goes simplification from 13 to one part. This is enormous simplification in every aspect of the system. Also, the lead time of this sub-assembly goes from 26 weeks up to only 3 weeks, the lead time. So it's very robust impacts on all the supply chain. That if we are speaking now about industrial additive manufacturing, this is very robust change. And of course, we also can get, in this case, we get the 22% of the weight reduction. What you are seeing here, it's a serial production. It's not some prototype or a fixture and so on. It's real product that is in serial production. And of course, as we say, the overall function and performance was improved, and all of this designed in NX. Okay, so if we are talking about additive manufacturing and what is the driving is we can say it about these two vectors. The first vector is the Y direction. We need to reimagine products. We need to think new and don't think about technology that get us to think as we thought until now. We can scan to product, and this is the first movie we start with it. And of course, we can expand the performance with simulation capabilities. And of course, the cycle of the development within the production is getting very small. Also, the manufacturing. If we are speaking about additive manufacturing, we eliminate the old process like molding, like casting, and of course, the cost of the tooling of this process that is cost a lot, and the NRE that we need to invest, it's very high. The process we are eliminate if we are thinking about additive manufacturing. Also, we eliminate and simplify the assembly process, as you saw in the example that I showed before. And of course, these two vectors get us to the last vector that help us to rethink the business. We are not need to hold a lot of inventory. We can print by demand, and this is get the business very good business. So barriers that we are seeing today about on customers at every on the globe. The main is that customer work with different systems, disconnected process. So, for example, one process is taking place at design. The design for additive manufacturing is one software. The simulation for additive is the other software. And of course, we need to transfer data. We need to transfer files with the native file and so on between this data. And every transfer of between systems, we are losing that. We are losing data. And also, if we are not losing data, we are losing the ability to act fast for changes. So if the design may change, this whole process needs to take place with these several systems, and also all the chain start from scratch. So for example, if I transfer the design, a new design for the simulation software, you will need to do the meshing again, you will need to do all his capabilities from scratch. So this is one barrier that we are seeing. The second is related to the additive manufacturing process as process, and this is the challenges. The challenges is to get accuracy on the printing. The challenges is not to recoater collision that we are seeing on the shop floor, local overheating of parts, build failure, of course, building effective support. How you know from advance that the support that you build is effective, and also how to distinguish from ahead microstructure and defects on the parts. So this is the barrier that we're seeing. What Siemens is suggesting for as a solution for these barriers and challenges that we see is the digital twin thinking. The digital twin thinking and the solution of digital twin. That means in general that we are building a digital twin for the physical twin. The physical twin is here at the right, and the digital twin is at the left. So we are starting at the CAD, we are going to the CAE capabilities, and after we are very satisfied with the process and the phases that we do, we can do the handshake, a real and strong handshake with the shop floor and deliver the shop floor products that can be printed at the first time accuracy. Siemens do it with the leading of the additive manufacturing community, like DMG Mori, like HP, OS, Electro Impact, Stratasys, Triumph, of course, Materialize, and so on. Siemens is building a hub also. If we will have time at the end, I also show you something that Siemens is working on very hard on the last few years. Okay, and the technology, the main technology that we are supporting, it's of course, it's the powder bed fusion. We also call it printing in 3 axis. Also the multi-jet fusion that you are seeing here on the top, it's 3 axis technology. So we are supporting this technology. And at the bottom of the screen, you can see the 5 axis printing, like direct energy deposition, and also material extrusion. As you see here, it's also 5 axis solution. All can be achieved from an one system end-to-end. Okay, I will skip this and I will dive for the first layer that I want to present. As I said, we are suggesting a full solution end-to-end from the design through the simulation and goes to the 3D printing. And this is what we are going to see. What is the tools that help us to achieve these goals? So from the design aspects, we have a lot of tools to do import and do the preparation, so they can help us to print at the end of the day watertight parts that will be print well. The second is design with convergent modeling. I will present the convergent modeling technology. This is a trademark of Siemens. and I will explain more what does this mean. Of course, lattice structure. What we can do with lattice structure in NX. Also optimize of lattice structure. The next will be design rules for manufacturability. How we can check that the parts that we are designed for printing, for 3D printing, can be produced. And we will also we'll see the capabilities to use the topology optimization in NX. I will focus on the topology optimization for the mechanical designer. We also have capabilities for the simulation designer, simulation engineer, and we will focus on the mechanical engineer aspects. So before we will dive, just to know that we are support all process, all workflow for printing, starting from prototype, that you have a simple design, you want to prepare it to printing, and you will print it. The second process is what we call scan to print, and this is what I start in the beginning of the presentation. We can scan parts. Import them into NX, and then take them to simulation, modify them very quickly, and also prepare them for printing and print them. And the last process, the last workflow is that we are taking from the beginning, where we want to take parts that today are designed with conventional thinking, like also we saw at the beginning of the presentation, and take these parts and optimize them so they will be more lightweight from mass concern, and also will be more robust for the process. So we are support all this workflow that refers to the 3D printing area. Okay, so if we are looking at the first tools, the set of tools that can help us to import and prepare prepared parts for 3D printing, we are speaking about capabilities of NX to work directly with geometry from legacy system. We can read topology optimization from other systems. We can read a CAE or scan data. For scan data or topology optimization and everything, we have very robust tools like polygon modeling. So polygon modeling is deal with all the faceted data, STL, for example, but not just STL, OBG, and other files that produce faceted bodies. We have, you can see here at the bottom, the set of tools that we have to deal with these faceted bodies. Like clean up faceted bodies, fill hole, wrap mesh, plug leakage, and so on. You will see some example in a few seconds. We also have a very robust tools for data healing and solidification. Of course, we have tools for reverse engineering and realize shape, subdivision modeling. Subdivision modeling, its capability to take faceted bodies and edit it directly in NX. And of course, the very strong technology that's called synchronized technology that also doesn't care from which source the data is came. It can edit directly the data and regardless of the source. So this set of tools can help the designer and everyone that wants to print and everyone that wants to do a 3D printing very easily to manipulate the data and control the data in a very efficient way. Let's see some examples. So the first example,
effectively working with multi-faced.
The first example you can see here that we we get data. This data is involved of mesh data, like you see here, and precise data. And what we will see, I want to will make the movie that will go faster, and you can see very fast change to mesh data. So this is what you see here. It's polygon modeling. We are inside of an X. We get something like STL. And for example, if we do a remesh, take this whole area. This area is maybe more important or less important. We can control the triangular. And for example, here we want to say that this area is more important, and we want to remesh it to finer element. And as you see, click button, and everything is fixed. Okay, another capability in the same concept is to divide face. Again, select area. You can use the brush. This is here a rough brush, and you can say this area I want to divide it because this area is important, and I want to close it with surfacing, do a newer surface, and so on. And then you see the face is divided. We are working on convergent body. When we are getting a part, SCL or OBG or something like that into an X, we doing a transformation to a convergent body. And now the system, you can see, we can simply do holes. Holes, it's a native operation of every CAD system, and also of an X, of course. But what you are seeing here, also I want to that you will understand it. We're doing an operation, a native operation from the CAD system, from an X on non-native data and mesh data, very easy, as you see here. It's thanks to the convergent modeling technology. Okay, this is direct editing, and how I think you understand the point that we can fix very fast data that came from other system or from within an X. Another capability I want to show you, this is also a new capability. We can take data, 2D data. What you are seeing here, it's a 2D data, spread on UV grid, and we implement it on a 3D data. So we tell the system, take this 2D data, put it here, please. You can see in what surface the system is doing it, and do for us an offset. This example, 1 millimeter, and the system will complete it. Okay, I also will run it. I want to show all of the most important capabilities. Another capability is to define and to validate the data that we get. For example, we get a data, we get the scans, it's STL. We are running a simple check here that we are telling the system, please find us what is not good with the scan. And we're getting it with a visual notification. So we can take this geometry, we can run a plug leakage test, and ask for the system to tell us, please let us know from which or from where we have leakage. So the system will run the analysis. And the system show us also visuals here. You have a leakage. The leakage was defined by a 2.5 millimeter. And of course, we can define whatever we want. And on the fly, you can see here the repairment. So on the fly, we have the same function, patch. We can do the draw boundary function and very, very easily close these gaps. Okay, of course we can do the check again, the plug leakage, and see if we have another leakage, and if not, we can go to production or continue with the part to the next level. Okay, the next topic I want to discuss with you is the convergent modeling technique of Siemens. The convergent modeling, as you saw from the previous slide and movie, its ability to work directly with faceted surface. Also, we are now having a capabilities to combine faceted bodies with precise geometry, as you saw here. Why we need these capabilities? Because this area, for example, it's very precise area that after the printing needs to go for machining. And get here accurate tolerance. So after the printing, we will get it to the machining. If we have here all this body was a mesh, we will have a problem to do here the machining. So from advanced, Siemens give us the capabilities from the topology optimization that you will see in a few seconds to generate these parts that involve with mesh scans and precise geometry. And as you saw earlier, we can also take this convergent and do a Boolean operation like subtract. We can do a Boolean operation of unite. And the main issue here that we are not need to do a reverse engineering of the part. Okay, it's very important to understand. It can be very exhausted to do a reverse engineering on parts, and this technology get us directly to the design. So the convergent technology is not only at the 3D printing, but also in every aspect of NX. We see it on the machining, we see it on topology optimization. And what is also important to understand that we can also take the result of the convergent bodies and continue with them to the next steps, like simulation, finite element analysis, for the assembly, for tooling, for documentation, drawings, and so on, and motion volume capabilities. This technology is implemented very hard at all Siemens products. And of course, if you want also, you can export it by step 242 and get it to any system, any other system if you want. Okay, so I want to show here one more example, how we are dealing with this convergent body. Also, this convergent body came from a topology optimization. Maybe the topology optimization wasn't so refined in this area, and the designer want to take this area and make it more fine, more robust. In a fewer click button is doing his design. Is using advanced capabilities of NX called realized shape. He can control the geometry, like you see here with cage. And after he is satisfied with the design, now we can say very quickly, please unite the convergent body to the design that I made, and he have a new design. Again, without reverse engineering. Without reverse engineering, this can be proceed to the next stage. Another example of convergent body is to take this example for this call example that also was scanned, get into NX, and you can do here a very quickly a patch on this area and continue working with, again, native tool of NX like extrude, like remove material very fast. And of course, everything is associative. Everything is associative during all the process of the chain within the CAD, the CAE, and the CAM. Okay. The next topic that I want to speak today, it's the lattice capabilities within NX. Lattice is used for lightweight component and also for structural integrity. So we are seeing these lattice capabilities, of course, with the 3D printing capabilities, taking more place and taking more of account. We can do a complex geometry and replace such areas that are not functional and can be with lattice very quickly. So this is the problem. Okay, yes, to get a more a lightweight component, and this is achieved with lattice capabilities. In NX, it's very easy. It works like 1, 2, 3. You need to select the unit lattice cell. You need to select the two. It's to select the solid volume and apply it what you want. Let's see an example. So we call the lattice. We select the geometry that we want to be filled. This is the function. We are calling unit lattice cell. We have something like 15 out of the box lattice defined within NX. But of course, we can also create a lattice. I will show you in a few seconds how we can do it in very complex way. Of course, we can control the randomize. We can control the row diameter and other aspects. And what is also need to understand here that the result of the lattice, it's also a convergent body. So we can transfer it to the manufacturing as separate bodies. And NX works natively with multi-bodies. Okay, not every CAD system work fine, work native with multi-bodies. In NX, it's the architecture to work with multi-bodies. So this is one example, and of course you can see from the industry a real example. And I want to show you another capabilities of the lattice. The lattice in NX is taking place in two manners. It can be take place on surface, and it can be take place on volume. What you saw in the last movie, it's work on volume. Now we'll see example to do a lattice on surface. So let's see it. So we select the face and we define the parameters and we get the lattice. So if we are seeing that the lattice, the convergent, it's not so fine, we can do a simple remesh. And the system will calculate. We can do a constant, we can do a variable, and the system understands the geometry, and according to their geometry, we get answers. This is a surface lattice, and another capability is to do a Teotodron fill. This is also work on the volume level, and you will see immediately what is happening here. This is more computed time. It takes more computed time. What you are seeing here, it's a real computed time with no manipulate on the movie. It's a real computed time. And this is what we achieved. Now we will do a hide for the geometry. And we will see only the lattice. The volume lattice, the Theodorus field. This is what we get. And of course, as I said, we can leave it as a separate body. It depends on the manufacturer. Mostly the manufacturing like to have it separately because they have a different definition of the lattice. But we can also do a simple unite as you saw before. And this is the result. A new capabilities that take place at the last version of NX, its capabilities to do optimization. To do optimization of the lattice. It means that I can define as a mechanical engineer a lattice body, a lattice fill unit as I showed earlier, and you can see it here. But I can ask for the system to give me the optimized lattice. So this is in the beginning, and this is the after the optimization. Let's see how it take place.
A load of 3,000, which is close to 660 pounds applied on the.
What you are seeing here, it's the CAE environment that is embedded in NX. It's called SimCenter, but it's embedded in NX. These parts came from NX. The lattice produced in NX, and in a click button, we are going to the CAE environment.
And gravity being applied, and these two are the constraints.
What is explained now that we are seeing the loads that taking place here, we can see the boundary condition that taking place here, and
on this part.
Let's see what happened.
And we have a lattice here, which is in terms of we have it in terms of a beam collector, that's the term used in the CAE. And I can just show the diameters of that by just bringing up the mesh display. Solid. So this is currently a constant diameter lattice. So user can just go in and say set up optimization and say I want raw diameters between these min and max values. And as soon as we do that, we get the linked file created in the backend, and it attaches it to the case after this.
Okay, I will
something
take the movie
we just have a off
viewer because
move beyond the command of just put
show
this
all the capabilities here. But in the end,
I can just say new values, and we did.
In the end, what you are seeing here is the optimized lattice that is suitable for this part. So you can define from ahead a lattice that you think that will be okay. And of course, you can validate it. And the system can give you an optimal.
See that displacement was of the surrounding body was within 0.01
variable
value.
Contribution.
And it again depends at various levels.
Okay. Another capabilities that is within NX, it's called NX implicit modeling. And this capabilities help us to do a TPMS structure like gyrod, like Schwarz, diamond, and so on. And let's see a short example. I want you to take focus on the mouse click that needs to take this geometry. Just a second. So we are selecting the volume that we want in this, and that's it. We have a new geometry with 2 clicks. We took the gyrod, Of course, we can also control the variation of the gyro and the offset and so on. But with 2 mouse clicks, as you see, we can do a gyro. Of course, also this can take to the CAE and analyze and so on. So that's it. Of course, we can validate it with native tools. We can do some sections. We can color it. We can do whatever we want. Also, this result is a convergent body. It's a convergent body. Okay, I will continue. Maybe we just this also with implicit modeling. It's another application. But we can also see the result. Of course, we can control the vectors, we can control everything. It's in the end of the day, all the things that I show you, it's function in an X that are associative, and we can call it back and change them in one click button. Okay, another capabilities we spoke before on lattice. As I say, we can.
Hello, my name's Paul Bevan from Siemens.
We can create a lattice structure of our own. This is with regard to a new capabilities in NX called the algorithmic modeling. This algorithmic modeling, you can see here at the top, it's called the basic function in NX, and is doing the connection between this function. Mainly, this capabilities taking place with codes like Visual Basic, Python, and so on. Today, we have these capabilities direct in NX, and you don't need to be a programmer to write the code. You can write a code, and the main benefit is that on your screen, you can see at the bottom what is taking place, what is happening. So you are doing the input and output, and I will proceed with the movie. And with random points, we can do and see the geometry that we can produce. So what is important to understand here, that we create geometry. At the end of the day, we create a part that can be reused. For example, for Veroni basic structure. Of course, we can collaborate it with our teams. And this is what we are seeing here. It's a function. It became a function in an X. Algorithmic feature, it's a feature. It's associative feature. And what you are seeing here, that this is the shoe that we have from before, we can now call this algorithmic that we was building before. And we can implement it very, very fast. As you see here at the left corner, Veroni basic. We can also add a picture if someone wants. And as you see, this is a function. And we can control the number of points. We can control the tube diameter and so on. And this is, the part is ready. Okay, this is another example. I want to continue to the next bullet. The next bullet is talking about the validation of the design. We have very strong tools to understand if the design that we made for the 3D printing, it's validated for 3D printing. So for example, we can check the wall thickness and see visualize of the wall thickness. We can do a check of the overhang angle. If we are printing metal parts, and not just metal parts, but it's usually on metal parts, we need to do a support. So the system can tell us, according to a work coordinate system, what is the area that will need support. We can also check the printable volume. If our parts, it's getting into the printing machine. We can check trapped support. We can check the area that is wholly enclosed volume, that if we are printing with powder bed fusion, we will get here a powder that can be get out during the process. So we need to, as a designer, need to think it from ahead. If yes, do a change in the design. If not, think together what to do. So this is the example. We call function in NX, for example, here check minimum wall thickness, calculate thickness, and we can see here that visualize, we can see the thickness. All the results are captured a tool in NX that's called HD3D tools, and is also associative. We can also share it, and so on. Here we do a check, an overhang check, sorry. Here we do an overhang check. All the validation take place relative to coordinate system, of course. For a specified, just remove it. For build plane, as you see here, it's specified build plane coordinate system. And according to this, the system do the calculation. And every validation like this, if we are happy with the result, the system can also produce a print coordinate system that continuous with the process, the manufacturing can use it. So check area of fully enclosed volume. Also, again, the result is visualized within green and red, as you see here. A simple check that we can put the part, the component at the print. And also here you will see, after the orientation will complete, a V remark that said that this is okay. Okay, of course, we can also define a trapped support. We do a trapped support. We can do a channel ratio support. We can do a lot of supports to understand if the design is proper for 3D printing. And for this example, we can see that this area will be a trapped support if this will be the print coordinate system. So we need to define what to do. Maybe to change the build plane, maybe to change the holes, and think what we are doing. Another capabilities, it's taking several of the tests that we saw before, like surface area, support volume, print time, and overheating in one function, and tell the system to do us simple part orientation optimization. So the system take place at surface area, support volume, print time, and so on, and get us a result. The part needs to be in this orientation, the part to be in this orientation. It depends on what we are selecting as a preferred criteria, like surface area, support volume, and so on. Okay, I will continue with the next topic. The next topic for the design for additive manufacturing is topology optimization. Topology optimization for the mechanical designer in NX, it's Siemens capabilities, and what you are seeing here, it's the process that starts with design, continue with construction bodies, define the objective for the optimization, define what is the shape that we want, and of course define the loads, define the constraints, and ask the system to do us the optimization. And finally we get the result. We can validate it with the same task environment, and finally get the result that we want. The result, as I said before, it's also a convergent body with precise area. Let's see here an example of it's in the latest months, it's very famous example. Here also the problem that the system of the engineering system tell us to take these 13 parts or something like 11 sheet metal parts and do with them one part. So again, we want to reduce the lead time. We want to reduce all the cost of the parts, and we also want to reduce the weight of the part. This is the goal. And we are starting to do an operation here. We define the design space. We define an area that will help us during the topology optimization, and we can get to the topology optimization task environment in NX and start a study. The study, as you see, we can call a maximum stiffness, minimum mass, and so on. And we have a navigator, optimization navigator within NX that we are controlling the design space. We're controlling, of course, the material. We can call an out-of-the-box material within NX. We can define the material, a new material. We are define the construction bodies, keep in, keep out, what will the optimization consider or not consider. If we want a maximum mass limit, we can define it. We can define the constraints and the loads. We define the fixed constraint. And we define also force at that area. And of course, this is a requirement of the system. We can also do a subcase manager. So in one study, we can get a multiply result of of subcases, of different subcases. For example, the first subcase is the force is going through z-axis, and the second subcase is touring minus z-axis, and so on. And in one study, here you see the active study, we can get several results. What you are seeing here, it's the result after the optimization complete. And again, it's convergent body with a precise area. With precise area because this area, it's a functional area. And this need to be assembled. This particular example need to assemble on a buggy on the car. So it could be also animate and see the results, the mechanical results. Okay, I will continue, and you, of course, you can compare studies and subcases. And again, this data is, as you see, it's a feature in NX. It's a feature in NX called topology optimization. Double click, get back into the topology, change parameter, and again, and do a very quick analysis. Okay. I will go to the second layer of the solution. The second layer of the solution is speaking about simulation. Of course, we will speak about the simulation of additive manufacturing. Yes. So let's see what we have here. So we talked at the beginning of the presentation about the challenges that we have with recoater collision, overheating, support failure, and so on. So Siemens solution for this, all the challenges, is to do a predefined simulation within the system, within NX. We can also do a powder meshing. We can do a support meshing and precise meshing of the geometry and get the result from ahead. And of course, also control the performance. So here you can see some examples of the powder meshing of the part. And what the system is doing, it's calculated the thermomechanical distortion of the part. The mechanical, you can see it here. We can also do a simulation powder, but the system will tell us where we have a distortion within the printing. So at the end of this process, we can predeform a part model, a new input geometry. We can tell the system, okay, we understand, this is the distortion that we'll have. Please give us back the calibrated geometry that will be print accurately. So we have all these capabilities within NX. I can show here two short movie. So in one click button, we are going to the simulation process. Here, of course, you can see the part, you can see the supports. We are defining a material, of course. And what you're seeing here, it's a thermal slice. We need to do a thermal slice. We need to do a mechanical slicing. Of course, also this could be a control with several of parameters. We can do a 3D tetrahedral mesh. Also thermal and mechanical. And what you're seeing here, it's the meshing of the powder, the meshing of the parts, meshing of the supports. And this was the first part of the simulation. It's the preparation for the simulation, of course. And what we see here is the computation. We run a computation, we call the solver, and this is the result. We get a result, distortion after printing, distortion after printing with the supports, distortion after cool down when we remove the build plate, and this is the result. We can also do, as you see here, after printing, after cool down, after support removal, and inspect the result with a visual bar, and see here thermal result, distortion, and do an inspection. Check the stiffness curves, local overheating, recoater collision. Do an animation of the build with the powder, without the powder. Okay, sorry. And the last thing here, we can check also the recoater collision. Tell us if we have distortion, in what area we'll have this collision. And maybe stop at the specific layer and do some adjustment. And of course, after everything is computed and we see the result, we can ask for a compensate model. Compensate model, and with this compensate model, we can go for the print. So this is what I want to show you today on the simulation. Simulation for additive manufacturing, and I want to continue to the next step. The next step is what related to the 3D printing themselves. So the preparation for the 3D printing is including the putting the parts on the build tray, on the tray content, orientation of the part, how to do a 2D in metal parts, and how to do a 3D nesting on the polymer parts. And how to build support, and how to create the build job, and so on. Okay, so this was the technology that you saw earlier. We spoke about three axes and the 5 axes. Of course, we have the solution for that. let's speak about the workflow for the 3D printing preparation for powder bed fusion. This is most widely used over the globe. Let's see some examples. So, what we have at the area of the preparation for the build. So we can position the part, we can create support, and define the build as we saw. Here you can see an example of the different supports that we have. Of course, we can build automatic support like you saw in the movie by right click, but we can also generate a manual support. For example, if we know that the automatic support it's not optimized, and we want to remove from one area and to build a manual support, we can do it. We can do several manual supports like block, point, line, and whatever you feel. You can also use a user-defined. And with user-defined, you can use all the capabilities of NX, the CAD capabilities of NX. And as you saw before, it's very, what you just saw, it's very robust capabilities. And you can create every support that you want. This is within the user-defined. And of course, we have also the out-of-the-box, like hybrid, what you're seeing here, tree, and other support that the system can generate very, very quickly. And also mentioned here, we mentioned the algorithmic modeling before. So you can build an algorithmic feature and call the user-defined and implement it as support. The support is associative, and if we do change in the build for parts, something like move the parts, rearrange the part, the support are associative and add it accordingly. Of course, we can also do a pattern for the support. I will show it in a few seconds. Here, I will continue with this, but this shows an example how we can control also the creation from ahead of the support. Also, I think it's important to know we can share support profile, compatibility with Materialize. So if you are right now printing with Materialize, we can import the support structure into NX, and you can use it. We have a support profile library, and you can manage the support profile library. It's traceable, and you can give access to for colleague and not give access for who can damage the data. So everything is also managed within NX, by the way, not for other systems, within NX. As I say, the support is associative, and so here you can see a pattern in different use cases. Also, part instancing and patterning include the support, so you don't need to do support for every part. You can take part, build him a support, and do a pattern, simple pattern. The patterning is a linear pattern, circular, polygon, spiral, along, and helix, and so on. I think it's enough. Generally, it's the patterning that are the building block of NX. It's native NX, and it's also in the 3D printing environment. Nesting, we can do a 2D nesting. We can control the Z orientation. We can control the rotation around Z axis, of course, and we can control also the overflow build array. So if we have part that getting out of the build, we can suggest a new overflow build. If we are speaking on polymer parts, we can do a 3D nesting. So we tell the system to put parts, to bring parts into the 3D printing environment, and then tell the system, please do a 3D nesting, that this is my specific printing machine, and NX will do automatic nesting and give a result. Also capability that we have the ability to do a print marks. In the industry, this is very important to do the serial number, so you can have a traceability, and you can know from each batch you produce the parts. So we have these abilities inherent in NX. You can do a text, simple text, and you control the numbers with an Excel sheet, and do only one, and the Excel will do the print marks by themselves. Of course, we can call the build strategy, and we can define the material, we can define the layer thickness, we can define the process setting, how the laser will work, in a lot of parameters of the machines, and all is again in NX. And if we are taking a look, an overview from the top, so this is the overview. We are starting with the design. As we spoke at the beginning of the presentation, you saw what is the capabilities to perform such design. After we are happy with the design, we validate it, we can put it to the environment of the 3D printing. We need to select the printer. We need to position the part. If we have several of parts, so also do a nesting, create the support, define the build process, verify the laser pass, and then get to the driver of the machine, and finally print the parts. Let's see an example. So here we are inside of an X. We are calling a Triumph print machine, for example. We are adding a component. We can reposition it with the work coordinate system. It's a dynamic, as you see, it's by dragging work coordinate system. Automatically create support, right click, create support. The system understands that she needs to build the support until the build tray. She needs to understand how to orient the part on the build tray. As you see, we have offset here from the build, and the support is created. Of course, we can change supports if we want after the creation, and again, we can do a manual creation of supports. For example, here we are doing a professionals on the block support, and now this is a different support. Here we can do a simple validation within NX, do a section, and review the layers. Here we are calling the build strategy. This part is example for aluminum. We can call the slicer. See if we have problem with the laser, if we have jump in the laser, if we have every issue on the 2D on each layers. And then print it. In this case, like this. Okay. The next step is to finish the part. Just to know, I don't think that for you it's important, but to know that we also have inside capabilities in NX called NX-CAM. It's also very huge capabilities to produce a CAM operations. For example, after we finish the printing, we want this area to be accuracy. So we put it on a milling machine, and we're doing this milling machine. And again, all is in NX. On can be with only file. One file that is everything is inside. Okay, the last, I want to show you another thing. For example, if we are printing in multi-jet fusion, so I want you to see here the capabilities of the nesting. For example, we can add the part as you saw before. And now we can tell the system, please do a 3D nesting calculation, optimization with different parameters, optimize the height, please finish after 1 minute. So we are doing here the calculation. This is a real-time computation time computer, what you are saying here. And that's it. The system gives us the 3D nesting computation. And from here, we are going again with the same process, select, the build, and so on. That's it. That's it for my side. Maybe you know what? I want to show you another, maybe the final thing I want to show you. It's this. You can see my screen, yes? Gershon, you can see my screen?
Yes, I can.
Okay. So I want to show you a part that is from a composite material that is printing in NX. You can see here it's NX. It's old version of NX. It's NX11, but you can see it's also in NX11. We can print 5-axis composite parts. So let's see it. So the system is building here layer by layer. And if we need to do to close an area that wasn't closed before, the system can also do it. Siemens developed on top of the NX-CAM, it's the capabilities of NX-CAM. NX-CAM, its capabilities that are in the industry is something like, I think, 30 years. And it's very strong capabilities for 5-axis machining, for blade machining, turbo machining. And on top of it, Siemens adds another capabilities for the 5-axis printing, as you saw here. And we can print composite parts. Okay, I think I will end here, Gershon. I think.
Yeah, thank you very much. I think it was very interesting, at least to me. I have some questions, but let's see if there are questions from other people before I will start. Okay, if not, maybe I would ask. I have two questions. One about, you showed kind of in the first part of the talk about a mouse with some details on top of it. You remember what I'm talking about?
Yes, it's the text. It's called the text capability. That taking the 2D elements,
right,
and implement it on the 3D mouse.
Surface. So my question is the geometry, the end geometry, is spline based or polygonal in this case?
Polygonal.
Polygonal. Okay, that's what I assumed. The second question that I have is, you have some support that is closed, like it has walls at the end, like the last part you showed.
Just a second. This one?
I don't know. Yeah, like the create support structure, the vertical support in blue looks kind of solid. Even though I understand there is some lattice inside, it has some walls. So what's the point of having walls around the support? I mean, you won't be able to take the powder out.
Yes, so So this is also can be controlled by the trap support. So we can validate and check if this is a trap support, and we can change the design. So we don't have the trap support. Also, we can perform a solid support, not just a block support. The block support is the out of the box. It's a sheet support, sheet body. But in several use cases, you need to build a solid support, something like to transfer the heat from area to area. So you also have these capabilities to build a solid support. But if you are asking about this specific area,
no, I'm talking about the big block. So
this one,
yeah.
Okay.
Okay, so it might be related to heat transfer. Yeah, that's a good point. So I don't know.
Yes.
Okay, any other questions from anybody else? If not, Netanel, thank you very, very much. It was very illuminating, and I'm sure we'll meet again at some point. Thank you very much.
Thank you, Gershon, and you.
Boaz, you're clapping. Okay, thank you. Okay, bye-bye, everybody.
You saw today.